Hi, everybody. My name is Taylor Vanderlinden. I'm a recent graduate of Florida State University with my bachelor's degree in biomedical engineering, and I specified in imaging and signal processing. My project for the summer was constructing a double resonant 33 millimeter inner diameter proton deuterium radio frequency coil, and I worked alongside Malathi Alumili. As a summary, I designed and constructed a double-channeled proton deuterium radio frequency coil for in vivo deuterium imaging. And throughout this REU project, I learned CAD, 3D printing, soldering, bench testing using a vector network analyzer, as well as doing deuterium phantom imaging at 21.1 Tesla. So as an introduction, radio frequency coils are used to transmit and receive RF signals to generate MRI images. The purpose of my coil design is to generate a magnetic field known as the B1 field, which is perpendicular to the main magnetic field B0 as shown in figure 1. The B1 field is responsible for transmitting and receiving energy from the subject that you are imaging. And the design of my coil, as I said, is double channeled. So there's a proton channel and there's a deuterium channel. The proton channel resonates around 900 megahertz at 21.1 Tesla. It's a birdcage design that creates optimal homogeneity in the B1 field, as shown in figure 2. What's unique about the birdcage design is that, in my case, it contains 24 legs, which has not been completed at the MagLab thus far. And the more legs a birdcage has, the more homogeneous your B1 field will be. And all of the other birdcage designs that we've done in the past had less than 24 legs. The proton channel also contains a sliding ring design that creates a wider tuning range for various loads. And the deuterium channel resonating at 138 megahertz at 21.1 Tesla, it utilizes a saddle design to create a homogeneous B1 field as shown in figure 3. The methods I use for constructing this coil include learning Autodesk Inventor to create various 3D printed components, as well as using a vector network analyzer. So I designed in CAD and then 3D printed a coil former and a phantom holder. The coil former was printed to lay out the saddle design for the deuterium channel, and the phantom holder was printed to center the sample in the coil for bench testing as well as magnet testing. Conducting bench testing allowed us to find the tuning ranges under various loading conditions, as well as determining the efficiency of the coil, which can be seen in table 1. In addition to this, figure 4 shows where the coil is resonating for both channels. We're currently still working on getting the proton to resonate in the right place at 900 megahertz. Currently, it's at roughly 864 megahertz. However, you can see that the deuterium channel is well matched at negative 35 dB. These are the results that I obtained from inserting my coil into the 21.1 Tesla magnet. I used a sample that contained a lot of deuterium, known as deuterium oxide. In figure 7, it shows the tuning and matching of the proton and the deuterium channels inside of the magnet, and figure 8 shows the deuterium signal. So you can see we're getting a very good deuterium signal. However, to enhance the quality of our images for the proton sign, getting it to resonate closer to 900 would be optimal. And figure 9 is the images of the sample obtained in the axial direction for both nuclei. In conclusion, my proton deuterium radio frequency coil prototype was tested on bench and in the 21.1 Tesla magnet. The prototype was able to handle various loads for the deuterium channel with an average Q value of 69.83. And the proton channel still needs to be fine-tuned to 900 under various loads. And currently, like I said previously, it's tuned to 864 megahertz. Future work, machining the 2H former or the deuterium former that will house the saddle design, making that out of G10 instead of a 3D printed material. Also fine-tuning the proton channel for accommodating variations in the magnet. So with the addition of the load from the probe and from the magnet itself, decoupling of the two channels, as well as in vivo imaging studies, including brain metabolism, stroke, and Alzheimer's studies. Some of the acknowledgements, I want to give special thanks to my mentor, Malathi, who's really shaped me into kind of being prepared for my future, as well as Dr. Grant and Dana Richter, one of his graduate students, and Joe Collins, machinist who I worked hand in hand with quite a bit at the MagLab. Thank you so much for your time today, and thanks again.